Okay, if you want to grab out your equation sheet, we're not going to have, we're going to have a few more equations we'll add to it this chapter. So this work equation is pretty fundamental to what we're going to be doing, okay? But there's a couple important components here that I want to make sure we kind of walk through. Force parallel is not what we think of when we talk about force parallel. It's not the gravitational component that's parallel to the incline, right? That was force parallel when we dealt with things on an incline. But here when we say force parallel, we're really just only worried about the force that is parallel to the displacement that's happening. So if the object is moving horizontally, I'm only concerned with the horizontal force, the horizontal component of that force. If the object is moving vertically, I'm only concerned with the vertical component of the force that's being applied. Okay, so we're talking about the force that is parallel to the displacement. Okay, does that kind of make sense? Okay, I want to give an even more broad definition of work as we walk through the chapter, but work can also be described as any change in energy that results from a net force. Okay, sorry, this is kind of hard to read, but, and this is my sort of definition, okay? It gives me a better picture of what's happening when we talk about work, okay? Work is any sort of change in energy that results from a net force, okay? If we have a force that's enough being applied, if we have a force that's great enough to displace an object, that means that work is being done, okay? Now, we're going to break it down a little bit more than that, but that's essentially the foundation for work, okay? Force parallel is the component that is parallel to our displacement. Okay, that's what we just kind of said here. In this case, our box is being displaced horizontally. And so we would use the cosine or the x component of that. I don't think this equation, like you need to write it down because you know how to solve for the horizontal or vertical component of a force. So you don't need to write down that specific example. But if my object is being displaced horizontally, that means I only am concerned with the component of the force that is parallel to that displacement. Okay, are we in agreement there? Okay, so force parallel. All right, so if I pushed a loaded grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart, how much work would I do? Right? It's as easy as it seems, okay? If I've got my grocery cart here, and I'm pushing it so that it moves 50 meters, and I'm applying a force of 30 newtons, I'm assuming I'm applying that 30 Newton force throughout the entire 50 meters, which means the work done. Are these two parallel to each other?
Yes.
Yeah, so all I'm doing is force times displacement. Okay, that's it. Easy peasy, right? Okay, so what is that, 1,500?
What do we measure that in?
Yep, so the units are, this is important, okay, this is really important. The units for work are Newton times meters. Newton times meters, and I want us to like highlight that, circle that, whatever you want to do with it, because we're going to start evaluating work on a graph. And so by knowing what units we need to come up with, it makes it a little bit simpler for us. So Newton times meters, okay? But realistically, that Newton times meters unit gets boiled down into what's called a joule, okay? And joule is the unit for energy. We've seen joules, like if you were in Chem 2, we talked about joules of energy or kilojoules. But joules is the unit for energy or work. So 1 joule is equal to 1 Newton meter. Okay? So I want you to really be kind of aware of that equation for work. If this is force times displacement, this has to be Newton times meters, okay, which is also called joules. But when we start analyzing work on a graph, this unit becomes really more applicable to us. But yeah, okay, go ahead.
So when we
Joules is fine. Joules is fine. Yep, but I'm just going to kind of keep reminding us that a joule is truly a Newton times meter. Okay, it's just a derived unit. It makes it simpler. Okay? Okay. So let's answer these questions here. Can work be exerted on an object, yet no work be done? I want you to think about these two questions, okay? I want you to think and then maybe discuss with somebody next to you. I'm going to give like 30 seconds. Can force be exerted on an object, yet no work be done? And what work is done on an object that's carried as I walk at constant velocity? Okay, so 30 seconds. Discuss amongst yourselves, and we'll see if we come to a consensus. I think we have a consensus on the first one. Can a force be exerted on an object, yet no work be done? Yes. True or false? True. Give me an example. Yeah. Okay, yes. I can apply as much force to this wall as I want. It's not going to move, right? And there's no displacement happening. So I can feel like I'm working really hard, yet no work is done, right? I could try and lift something off the floor, but if it doesn't displace, doesn't matter, right? So that's why I think the concept of work is tricky to me, because it can feel like we're doing a lot, right? We might be actually outputting a lot of force, yet we are not doing any work, okay? That's the difference. All right, what about the second one? I carry an object at constant velocity. Am I doing work or not? On the object itself, on the book. Is there any work being done?
Besides normal force?
Oh, yeah, besides.
Any work being done? No, not even normal force. Because why? Where's the book displaced? Horizontally or vertically? Horizontally. And how is my force being applied? Vertically. I'm applying a vertical force to keep the book up. So did I do work to lift it off the table? Yes. Right? Did I do work to push it across the table? Yes. But as I walk, or as it sits still, right, its displacement is horizontal, but my force is vertical. So I'm not technically, there's no work being done on the book itself.
So how's the book still moving sideways?
If it's not,
There's no work being done on it. The work that's being done is, there's work being done by gravity, and there's work being done by the normal force, but they cancel each other out. So the net work of that would be zero.
Okay, so you're not counting the work of the friction on your hands.
Right.
To keep the thing moving
From
forward.
sliding, yeah, no. All right, this one just explains that block. Okay, two things that we have to think about when we deal with work. We're going to have to specify whether we're talking about work being done on an object or by an object. Okay, are we talking about work done by my hand, work done on the book? Sometimes those values are equal and opposite, right? Sometimes those values are the same, but sometimes they're not, okay? That will become more apparent as we get into some problems. Second thing is that we have to specify whether the work done is due to a particular force or whether the work done is the net work, okay? Because those are two different things. We can find how much work is being done by gravity and how much work was being done by my hands in this case. They would have been equal and opposite because my object wasn't having a net force in the vertical direction. So work done by gravity would have been equal and opposite to the work that I was doing to hold the book up, right? And that would have given me a net work of 0. Okay, so we have to kind of specify what that's going to look like. Okay, so a couple different ways we can go about doing our problems. We can solve for the net force first, or we can solve for the work done first and then find the net, right? There's a lot of different ways we can go about it, but let's go ahead and try one here, okay? A 50 kilogram crate is pulled 40 meters horizontally along a horizontal floor. This right here is not a force component. It's showing the displacement. So I should have made it dotted or something, but I didn't. So that's showing our 40-meter displacement, okay? We're applying a constant force of 100 newtons at 37 degrees. The floor exerts a frictional force of 50 newtons. Determine the work done on the crate. So I want the net work, okay, because it doesn't say work done by something else. So I want the net work. Will I be focused on the horizontal components or the vertical components here? Horizontal, because it's sliding horizontally. So that means I need the horizontal components of this force right here. I don't need the vertical, but I need the X component there. Okay, so I'm going to go 100 cosine 37, and I get 79.9 newtons. Okay, we could go about this two ways. We could find the work done by this force for 40 meters, and the work done by this force for 40 meters and then solve for the net. But in my opinion, I think it's easier to just find, well, what's the net force? And then we'll take that times our displacement. So I'll leave that up to you which option you want to choose. But for me, I would just go ahead and set up my net force would equal my applied X minus friction. So 29.9 newtons would be my force parallel in this case, right? Because it's parallel to my displacement. And then to find the work done, I would take 29.9 newtons times 40 meters. And I would get 1,196, what? What do I measure it in? Joules. Yep, capital J. Okay, because I wanted the net work done on the system, right? We have an applied force that's causing our box to accelerate, which means we're going to have work being done, right? So our net work here is causing it to move. That a hiker must do on a 15-kilogram backpack to carry it up a hill with a height of 10 meters at constant velocity. Okay, we want the work done by the hiker, only the hiker. Okay, so if I'm looking at the backpack on the guy's back, right, I already drew the free body diagram here. If I want the backpack on his back, is it accelerating? No, right? On his back, essentially the backpack is at rest, isn't it? Right? And so if that's the case, the force that he is applying is equal to our gravitational force, right? He's just keeping it from falling. Would we agree with that, right? The force that he's applying is just enough to keep him from falling. Okay? So the force that he has to apply, the force of the hiker, would have to be equal to the force of gravity. Would we agree with that? Okay, so now here's, you guys aren't going to like this, but here's how it works. Do I care how the backpack gets from the bottom of the hill to the top of the hill?
Not really.
Not really, because he's applying a vertical force. And so I am only concerned about the vertical displacement that this backpack travels. The work is it's not what's called a path function. That means I don't care about the path it takes to get there. It could ride an escalator for all we care, okay? It doesn't matter how they get from the bottom to the top or from point A to point B, right? All we care about is the fact that this force was applied for 10 meters. So he could have zigzagged his way up the mountain. He could have literally rock climbed. Those would have felt like they were significantly different amounts of work. Would you agree with that? Right? Walking up a slow, winding path would feel much differently than climbing up, then riding an escalator to the top. But in reality, that's the same amount of work, right? The physics work that is being done is the same. That's the part that's frustrating to me, is that, like, it doesn't feel the same, but when you boil it down, it's the same. Okay, the amount of time it takes, that's a great question. That's going to be what's called power. So we're going to calculate how much power it took. That's work over time. Yeah, so we can calculate different power outputs, how fast you do the work. Yeah.
Can you have, like, negative vertical work?
If it's moving downward?
Like, if he goes up and he has to climb back down a cliff and then go up, would that cancel out? Because
you're just looking at your overall vertical displacement. Yeah.
So essentially work isn't the same as effort?
Correct. Work and effort are not the same. Yep. Yeah, Isaac.
Can you solve, so like if we wanted to know how much work overall was done on this thing, can you solve horizontal and vertical and just add them, or how do you?
Not a concept we usually do, but I assume you could do vector addition with it.
Okay.
Yeah. Work, I guess, maybe I shouldn't have said that.
How much work total does it take me to go up this 10-meter hill if I start 40 meters away? Like,
you're still just looking at a vertical rise.
yeah, but you have to go this way too.
Right. You're still walking horizontally is what you're saying. You're putting out a horizontal.
Pushing a ball up a 10-meter hill.
No, it pretty much doesn't matter. You're just looking at your start and your finish. Yeah. Okay, so sorry, let's keep going here. If we know the force of the hiker is the same as the force of gravity, we would take 15 times 9.8, and we get 147 times 10 meters, which means 1470 joules. All right, that's how much work is being done just by the hiker over that 10 meters. Okay? Now, okay, yeah, I don't know why I did that. Okay, now find the work done by gravity. What do we think? It's the same, right? Because during that whole time, gravity was being applied, right? So the work done by gravity is the same in this case. So 1470 joules, which means the net work is 0, right? Okay, because the backpack itself was not accelerating. That could have been our easiest clue, right? The backpack itself was not accelerating, so it would have been 0. 0 joules. And how they're connected. There are a lot of different types of energy and categories of energy, but we're going to focus on kinetic and potential. Have we heard those terms before? Kinetic energy and potential energy. What does kinetic, what's that prefix mean? Kina. Objects in motion. So kinetic energy is energy of objects that are in motion. And then potential energy, what do you think that might mean?
It's like energy stored.
Yep, it's stored energy. It's what it has the potential to do. And so we're going to look at two main categories of potential energy. Gravitational potential energy, when things have the ability to fall and make something do work. And spring potential energy, so energy that's stored in a spring or a coil, things like that. So those are two types or categories of energy. So the most basic of definitions for energy is the ability of an object to do work. Okay, the ability of an object to do work. So that means they've got enough energy stored to apply a force to something to make it move, right? That's what energy means. Does it have enough stuff, right? I don't want to keep using energy in its definition, right? But does it have the ability to apply a force and make something move, right? That's what we're looking at, okay? So we're looking kinetic energy first. It's the energy of an object that is in motion. Kinetic energy is transferable from one thing to another, right? When we see a perfectly elastic collision, we see a perfect transfer of kinetic energy. Okay, I want you to give me, can you think of any examples of perfect transfers of kinetic energy? Yeah.
Isn't Newton's cradle?
Yeah, Newton's cradle. You know what I'm saying? The little desk toy where it's got like 6 balls in a row and you hit it, it bounces, right? Right. That's a perfect transfer of kinetic energy. They go from rest, right, to now being in motion. Now this one goes to rest. This one's in motion. Blah blah blah. If you played pool, right, perfectly, right, that would be a perfect transfer of kinetic energy. The cue ball should come to rest when it hits the other one, right? That's a theoretical perfect transfer of kinetic energy. But that's what we're looking at here, okay? So kinetic energy is the equation 1/2 mv squared, okay? A lot of times you'll just see it listed as K, or even your E is a little subscript here. But AP uses K for it, so you'll see that kinetic energy. 1/2 m, what do you think the m is here? Mass, and then V has to be velocity. Okay, yeah, go ahead.
Is it 1/2 mv squared or 1/2 mv squared?
Just the V is squared. Just velocity is squared. Okay. This is also measured in joules. Also measured in joules. Okay. This is what's called translational kinetic energy. When you translate something like in geometry or on a graph, what's it mean?
We just move it.
It just slides, right? It's not rotating. Okay, so rotational kinetic energy is a little bit different. So that would be things that spin on an axis. These are just things that move, okay, or slide, or they can move in a circle, but not things that are in rotational motion just yet. Okay, so 1/2 mv squared. That one should go on your equation sheet as well for kinetic energy. So these are energy of objects, of things that are in motion. All right, we are able to connect work and energy. Okay, this is called the work energy principle. Cleverly named, okay? Work energy principle means that the net work on our system is equal to the change in energy. Remember how at the beginning I said work is any sort of energy change? It can apply to potential energy as well, but we're just not there yet, okay? So work is equal to the change in kinetic energy, Okay, the amount of work done is equal to change in kinetic energy. So you could put that as final and initial if you want. Whatever you want to do, it doesn't really matter. But change in kinetic energy, this guy needs to go on your equation sheet as well. Okay, so we are able to find the work done, possibly without knowing the force, right? If we're just able to know how much its velocity changed, we would be able to find out how much work was done on our object. So now we've got two different ways that we can solve for work. Okay, two different ways. Okay, so if they're both equal to work, what can we do to them? You can set them equal to each other, right? If that would be the case, right? If we know that work is equal to force times displacement and work is equal to change in kinetic energy, there might be situations where we do this. Force times displacement equals change in kinetic energy, right? We can set them equal to one another. Not always the case, but we have to be creative here with our equations, okay? All right, this equation only works when we're looking at net work, not just the work done by a singular force, okay? Yeah, go ahead, Brennan.
Oh.
How do you know that our 45.3 was the final velocity?
Because it wanted to know how much work was done to make it reach this speed and if it started from rest. So we were examining the work done from rest to that point.
If we had, like, I guess, another,
Second. So how much work is done? 1/2 m. And then we have to be careful. Does 20 go first? 1/2 mv squared. It needs to be my final velocity here. So 1/2 times 1,000 times 30 squared minus 1/2 times 1,000 times 20 squared, right?
A lot of work.
Seriously.
Okay, I'm going to rearrange our slides here just a little bit. The next slides that you have talks about power. I'm going to skip over that for just a second, and we're going to go to potential energy. Okay, so let's slide over. To this guy. Okay, so we're going to come back to power within the next day, but I want to get through potential energy. Okay, so let's move into this next one. So we've talked about kinetic energy. That's our object in motion. Potential energy is stored energy. Okay, I want you to just write this out. It's stored energy. It has the potential to do work on something else. Okay, so we're going to start with gravitational potential energy. Now, I'm going to give you a little warning here. I have always learned and always written potential energy just like that, PE. But for some reason, which is unbeknownst to me, AP uses U as the variable for potential energy.
why?
I don't know why. Maybe other people use that. I've never seen that before. So I'm just telling you, I'll mess it up, but you need to write U, and I'll try to do a good job writing U for your equations, but U represents potential energy. So I'm going to do my best, but I'm probably going to mess it up, okay? So the U is going to be the variable for potential energy. I don't know why, okay? So the first type of potential energy we're going to look at is potential energy due to gravity. So this would be UG, potential energy due to gravity. So this means, okay, it says when a heavy brick or anything, doesn't have to be heavy, when something is held into the air, it has potential energy because of its position relative to the earth. So let's think about what's happening here, okay? So I'm holding something in the air, a brick, something, whatever. And let's say there's a nail in the ground, just kind of sticking up. When the brick hits that nail, what will happen? Will the nail be driven into the ground? Yeah, right. Because it's applying enough force to displace that object, right? It has the potential to do work on whatever's sitting underneath of it. So potential energy due to gravity has to do with the object's mass and the height it is above the earth. So the higher something is, the more work that could be done on an object that it falls on. Does that make sense? That seems like it's intuitive, right? Okay, so that's potential energy, okay? And I guarantee you I didn't fix these slides. Yeah, I thought so. Okay, so UG, potential energy due to gravity is equal to mgh.
So,
Excuse me, work is still equal to any sort of change in energy. So we can apply the work energy principle to potential energy as well. Sorry.
Does this word net or word?
Yep, still net. Yep, sorry, I didn't include that, but you're right. So there's a lot of different ways we can solve for work. I like to think of work as just any sort of transformation in energy, right? Did we have a change? Yes or no?
I don't really like
Okay.
work.
This chapter and this section loves to use roller coasters. Loves. Okay, we do all sorts of situations on roller coasters. Yeah, no. Now I just want to look at how energy is changed from one thing to another. So at the top, right, to get to the top of the roller coaster, what has to happen? Can you get there? Okay, let me think about this. What happens at the beginning of the roller coaster, the big ones?
You have to go.
You have to go, you either start yourself at the top or click, 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 right? A motor takes you to the top. But at that highest, at your start, isn't that typically the highest point you get on the roller coaster?
Yeah.
Unless a motor takes you higher, right? It's playing out physics principles right there. You're getting as much energy as you can by going as high as you can to start. And then you ride all that energy out all the way to the end. The only way you could go higher than where you started is if a motor takes you click, 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 even higher, right? You know what I'm saying? So that's why you start the roller coaster with the you know, and it's like I would be puking on the way up, okay, right? So, you know, on the slow click, 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 not for me, okay? But that's how you gain that potential energy, and then you're able to ride that energy all the way out. So as it reaches the bottom point right there, we've transferred all of that potential energy into kinetic energy because now we're in motion, and we're assuming the safety of the roller coaster here, we're not going to fall any further, right? The bottom of the track we're considering like our ground level, right? We don't have any potential to go any further downward. So we've transferred all of our energy to kinetic. But any point in between those two, you have both types of energy, both potential and kinetic, because you're off the ground, so you've got potential, and you're in motion, so you've got kinetic. So any point between start and bottom, you would have both types of energy. Does that kind of make sense? So we're going to look at how those are connected here in a little bit, but not right now. Okay, so we take point A, right? That was our relative starting point. Then we went up 10 meters to point B. So at point B, we have mgh to give us 98,000 joules of energy. Okay. So the calculations part of this chapter is very easy, but the tricky part is seeing how everything fits together, right? How energy and work and all that stuff fits together.
It's the same amount to get to the top of the hill as it would be to get back down to A.
You would lose 98,000 joules of energy to get down to A. You would lose that many joules of potential energy, but it would be transferred to kinetic energy,
90.
right? We would move that into kinetic energy or thermal energy if there's friction.
How does that transfer?
Well, that's the whole principle of it, is that energy is conserved. It doesn't go to nowhere. It gets changed into a different form. It becomes speed, right? Yeah.
I understand like the mass and the height, but I don't get like, is it the force of gravity, the potential energy
It's
of
an
gravity?
acceleration due to gravity. Little g is 9.8.
Gotcha.
Right, so that's the acceleration due to gravity. But look, think about what we did here. mg is the force of gravity that's being applied. That is mg times the height. Doesn't that look just like the equation for work? Force times displacement, right? We're doing the same things. We're just applying it in a different thought process. Okay, we're still looking at what is the work happening from here to here.
You can just automatically make A 0 because it's at height 0, right?
For right here,
So yeah, for this one.
your A would still be 9.8, but height would be 0.
Right, but like when we're talking about
Oh, if this was my ground level, my potential energy at A would be 0.
Yeah.
Right, exactly.
We're making it relative to point.
Exactly. Yep. All right, a jogger runs up a flight of stairs. We haven't done the power yet, so keep that. Oh, no, we haven't done power yet. Oh, I've skipped ahead, and that's when I... Okay.
There's another like Elastic potential energy.
Let's keep moving. I want to do, yep, the only last thing I want to do is, I did the wrong thing here. Move over to spring. So we're going to get power all at one time tomorrow. So the last thing we're going to look at here is potential energy of springs. Sorry, I moved these around in my head, but I didn't move them around in the slides. All right, so potential energy of springs. There's a couple different like vocabulary terms I need you to be familiar with. What does the word static mean?
It's just kind of sitting there.
It's at rest, right? It is not moving. So static, if something is static, that means for a spring, it's considered at equilibrium, okay? It's just resting. So that's its resting spring. Compressed means we're pushing it together. Stretched means we're pulling it out. Are we good with those vocabulary terms in terms of the spring? Yeah. Okay. So a spring potential energy is given US for a spring potential energy, and it's 1/2 kx squared. 1/2 kx squared. So K is called the spring constant. Okay, which is deceiving because it's really not a constant. Every spring has its own spring constant. Okay, dependent upon how springy it is.
It's
Okay.
like the coefficient of friction.
Essentially like the coefficient of friction. So what's the toy? Slinky. Okay, Slinky has very low spring constant. But shocks on your car, very high spring constant, right? So spring constant depends on how springy it is, right? How much force is required to displace it. And then X is the distance that the spring has been stretched or compressed from its static position. So let's see, let's draw it. This is the situation in a lot of problems, right? We've got a spring attached to a wall. It always tells us that, so that we know the spring can't move side to side, okay? But it's attached to a wall. If I stretch that spring out, this value would be X. The difference from equilibrium position to stretched position would be X. A lot of times that X value will be given to us in like centimeters because you don't stretch meters very often. You can't stretch a string meter. So that has to be converted because we do want X to be in meters, okay? Again, just the X value of it is squared. We want that to be in meters. K value is measured in newtons divided by meters. Newtons divided by meters.
And X doesn't have it? Or
X is meters. X is meters. Okay, because if we look at the units here, 1/2 Newton divided by meters times meters squared. That leaves me with newtons times meters, which is the same as joules. Right? Okay, so that's how the unit derivation comes about. Yes?
Are springs the only things that have elastic energy?
Yeah. I mean, anything that has bounce to it. Yeah. So rubber, bouncy balls, things like that. Anything that have that bounce factor, right?
Like roller skates.